This video is to get you started on your rational functions and limits worksheet. So I want to start by reviewing what we've learned so far about rational functions and limits. We have the situation where we take the limit as x goes to infinity of a particular function. We can't exactly plug infinity into the function, but we sort of imagine plugging a very large number in for x, and we know we have three different cases. If the numerator has a degree higher than the denominator, when we plug it in, y just goes to infinity. In that case, we have no horizontal asymptote. Or we could plug, if the numerator has a lower degree and the denominator has the higher degree, then we know that as we put in a very large number for x, y just goes to 0. So we have a horizontal asymptote at y equals 0. The third case would be that we have a non-zero number. So this is when the degree of the numerator and the denominator are equal. We get some non-zero number for our horizontal asymptote. So we still have a horizontal asymptote. Y just equals a number. So this is where you're looking at the degree of the numerator, the degree of the denominator, seeing if which one's bigger or if they're equal. So this is the same thing we did when we graph rational functions, that we're just including now a number in here. We're just including limit notation. Now the second type of limits we did was x is a particular number. I'm saying what happens as x goes to -1? What happens as x goes to 5, for example? You're going to always start, number 1, find f of c. In other words, plug the number into the function. And you're going to get one of three cases. A, f of c equals a number. Okay? If f of c equals a specific number, what you found is that there is no discontinuity at that point. There's no discontinuity in the graph. And f of c is a point on the graph. If you find f of c and you plug it in, and you put in f of c and you get a non-zero number divided by 0, that tells me I have an infinite discontinuity. In other words, as x goes to that number, y goes to positive infinity. So y is going to positive or negative. That's not what I meant to write. Y approaches positive and negative infinity as x goes to c. And so we have here a vertical asymptote. So whenever you see the 0 in the denominator, you know there's a discontinuity. When there is not a 0 in the numerator, when there's something else in the numerator besides 0, we have a vertical asymptote. The vertical asymptote is at x equals c. In other words, this number here, whatever, as x is approaching that number, that's where our vertical asymptote is. If we do f of c and we get 0 over 0, that tells me I have a hole, which is known as a removable discontinuity. When I have a removable discontinuity, I'm going to find factors by dividing, cancel the common factor, and take another limit. So I'm going to take another limit, and f of c is then going to be the hole in the graph. So in other words, as x gets really close to c in this case, y is getting really close to a number, but the actual number can't exist because there is a variable in the denominator and I'm not allowed to have the denominator equal to 0. But I can cancel it out and divide again and find out what it would be like if that number existed, basically. So looking at this, what we're going to do with our worksheet here is I'm going to give you some different limits, and and you're going to look at the different cases. So we'll go through the first couple together. when we look at this first one, we see the numerator is bigger than the denominator as far as degree. If we put in a really big number for x, this is going to get close to 0. So this tells me I have a horizontal asymptote at 0. The limit is 0. Here we have as x goes to 5. Well, if there's a specific number, I have to plug it in. So I'm going to say 4 over 5 minus 5, which is 4 over 0. Remember, we have a non-zero number in the numerator, a 0 in the denominator, which means we have what's called an infinite discontinuity. This is a vertical asymptote. So I have a vertical asymptote not at 4. The numerator doesn't tell me anything, but at 5, because it's still what we did before. 5 is what makes the denominator equal to 0. So here's my vertical asymptote. Now, here x goes to 6. I plug in 6 and I get 4 over 1, which is 4. This tells me there's no discontinuity at that point. There is no hole, there is no asymptote. This is just a point on the graph. So a point on the graph is 6, 4. I could plot that number. 6, 1, 2, 3, 4. So, hey, that helps me out, because that tells me I've got my graph is going here. I don't have any x-intercepts. My y-intercept is negative 4/5, which is down here, so that tells me my other part of the graph is here. So when I say what feature corresponds with each one of the limits, so when I have the limit as x goes to infinity equals 0, that tells me I have a horizontal asymptote at y equals 0. The second limit, I plug in 5, I get 4 divided by 0. This tells me I have what's known as an infinite discontinuity. Infinite discontinuity. And this is a vertical asymptote at x equals 5. Then the third one is no discontinuity. It's a point on the graph. Continuity, let's make sure I spell that right. X equals, or sorry, the point 6, 4 is a point on the graph. Now, what I'm going to ask you to do as we go through these examples is to go through and you can just calculate the limit, and then you can just write this information right next to the limit. But the first two I gave you blanks to put it in so that we could practice. Okay, here we have a little bit more complicated looking situations. First, infinite, put in infinity. Here we have the degree of the numerator, the degree of the denominator are equal. That means that if I put in a really big number for x, this is just going to level off to 1. So this is my horizontal asymptote. So I'm going down to number 1 down here, horizontal asymptote at y equals 1. So I'll plot that. Now if I put in negative 2, I get 4 plus 8 plus 3. So negative 2 squared is 4. Negative 4 times negative 2 is plus 8 plus 3. Then I get negative 2 squared, which is 4, minus a negative 2, which would be plus 2, minus 6. So I get 15 over 0. That tells me I have what's called an infinite discontinuity. In other words, I can't fix this one. I cannot remove it. This tells me I have a vertical asymptote at not x equals 15, at x equal negative 2, because negative 2 is what makes the denominator equal to 0. Now, if I factor this, I know then this has a factor of negative 2. As a matter of fact, I could factor, a factor of x plus 2. This is x plus 2, x minus 3. And in fact, in my numerator, I could also factor that. But there's where that's coming from. Now, notice the other number I'm plugging in is the 3. So what happens when I plug in 3? I get 9 minus 12 plus 3 over 9 minus 3 minus 6, which is 0 over 0. This is what's known as a removable discontinuity, and so I need to remove it. That means I have a hole. Where's the hole? Okay, so what I'm going to do is I'm going to recognize that I know I have a factor of x minus 3 in both the numerator and the denominator, because 3 makes both the numerator and the denominator equal to 0. So it is a 0 of both of these polynomials. Therefore, both of these polynomials factor to have a factor of x minus 3. So there's an x minus 3 here. I already know from before there's an x minus 3, and this is x plus 2. The other factor here would be x minus 1. So how do I remove my discontinuity? I cancel the common factor. I redo the limit without that troublesome factor in there. Now, does the graph just look like x minus 1 over x plus 2? Yes, it actually does. Whatever x minus 1 over x plus 2, the graph looks like that, except it has a hole in it at 3. I plug the 3 in now, and I get 3 minus 1 over 3 plus 2, which is 2/5. So that tells me my hole is at 3 2/5. So this is the y-coordinate of the hole. The x value is the 3. So I know I have a hole at 3 2/5. Let me see if I can get this to scroll down again without scrolling up too much. Okay, 3 2/5. 1, 2, 3. So that's about right here. There's my hole. If I look further, I can look back at my function. I have an x-intercept at 1, because this isn't an x-intercept. When you cancel out the factor, it's not an x-intercept, nor is it a vertical asymptote. So I have a x-intercept at 1, and I have a y-intercept. If I put 0 in every place there's an x, I would get I get 3 over negative 6, or negative 1 over 2, negative 1/2. So my y-intercept is negative 1/2, which is right here. So you can see that this part of the graph is going to go down like that. Then I just need to pick a point over here. If I put in negative 10, if I put in negative 10 here, that would be negative, that would be negative, so it would be positive, a positive number. In fact, that would be negative 10. Negative 11 over negative 8, which is bigger than 1, which means I'm going to be up here somewhere. So this part of the graph would be up like that. Okay, so this is basically what you did before with rational functions and rational functions, only now we're just saying if we can do a little more complicated ones more quickly now, because if we plug a number in, we can quickly see by this part right here, vertical asymptote, hole. We can see the other asymptotes. If we plug in something that is not either, it's not divided by 0, like on number 1. If it's not divided by 0 at all when we plug it in, then it's just a point on the graph. Okay, I'm going to let you finish the other 3 yourself for homework.